Let's talk about forces. We'll delve into Cartesian vector notation and extend our understanding to three-dimensional vectors. The objectives of this section are that you should be able to represent vectors in a three-dimensional space in both Cartesian coordinate system and using coordinate angles. Lastly, given either of these situations, you should be able to add or subtract your vectors. There are many applications where the forces are in a three-dimensional space. Here are two examples that are typical tie-down situations. In fact, a system of tent-corner tie-downs is another example. In some cases, you may be trying to determine the total resultant force and its direction to make sure that the structure isn't off-center. Or you may have the total force acting on a structure, and you want to make sure that the force is distributed in a balanced way by resolving the force along multiple support wires. Let us first define the right-handed coordinate system. Place the pinky side of your right hand along the positive x-axis. Curl your fingers toward the positive y-axis. The direction your thumb points is considered positive. This perspective will come into play a lot as we balance our systems, so I suggest you really become comfortable with the right-hand convention. So we know about the xy unit vectors, but in the three-dimensional space, there's a third unit vector, k caret. That indicates the direction along the z-axis. The resultant of those three unit vectors, I, j, and k, becomes the unit vector u. So for example, to find the unit vector for some vectors, say a, you divide your vector a by the magnitude of a, and that gives you your unit vector u sub a. As a reminder, the magnitude of a unit vector is always 1. It's also dimensionless, and it only tells you the direction the vector is, so that's whether it's positive or negative. Suppose you have a three-dimensional vector with a magnitude of a. Here, the vector is represented by the a with an arrow, and the magnitude is just an a. Vector A has components acting along the x, y, and z axes. These are given by ax, ay, and az. To find these components, remember that vector A is equal to vector a sub x plus vector a sub y plus vector a sub z. Or, if we think about it in terms of Cartesian vector notation, then vector A is equal to ax times I caret plus ay times j caret plus az times k caret. To resolve vector A into its component parts, first recognize that vector A is comprised of two vectors to begin with along the z and the xy planes. Using the reverse of the parallelogram law, we can find the vertical component a sub z times k caret and a horizontal component, which we'll go ahead and call vector a prime. Vector a prime has a magnitude of a prime. A prime does not coincide with any axis, but it does lie in a plane defined by x and y. Therefore, now we can resolve vector a prime into ax times I caret and ay times j caret. The direction of orientation of vector A can also be defined by the angles it makes with each of these axes. The angles are designated alpha, which is the angle between the vector and the positive x-axis. Then you have beta, which is the angle between the vector and the positive y-axis. And finally, you have gamma, which is the angle between the vector and the positive z-axis. Now, because this is respect to the positive axes, the angle can range between 0 and 180 degrees. So it'll be less than or equal to 90 degrees if it's in the positive quadrant, but then if it's in the negative quadrant, then it would be greater than 90 degrees, okay? And again, that's because it's measured from the positive axis. Alpha, beta, and gamma are dependent on each other, and they must follow the relationship that the sum of the cosines squared of the angles must equal 1. Then the direction cosines are found from the relationship between the magnitude of the vector component and the magnitude of the vector. Now, I just want to be extra clear here, be careful, because this is with respect to the magnitude, not the actual vectors. Finally, the resultant unit vector can be derived from the coordinate direction angles and the unit vector. First, the formula for finding the unit vector of any position vector is given as, and this is in terms of A, so we have A sub x times I caret plus A sub y times j caret plus A sub z times k caret. If you divide each one of those by the magnitude of the vector, in this case A, then you can substitute the trigonometric functions that represent the direction cosines, and you would therefore get the unit vector, which is equal to the cosine of alpha times I caret plus the cosine of beta times j caret plus the cosine of gamma times k caret. Once the individual vectors are written in Cartesian form, it's very easy to add or subtract them. The process, it's basically the same. It doesn't matter how many dimensions you have. So in essence, what you're wanting to do is sum up the forces along the x, y, and z axis. So for an example, let's suppose you have two vectors a and b that you want to add. First, you resolve the forces into their I, j, k components. Then you add a sub x to b sub x, and that'll give you fr sub x times I caret. Next, you add a sub y to b sub y to get fr sub y times j caret. And lastly, you add a sub z to b sub z, and you'll get fr sub z times k caret. Now, it's important to realize this assumes that all the components are along the positive axis. So suppose you have one of the components along the negative axis. All you would do is change that particular component to a negative instead of a positive, essentially subtracting it instead of adding it. 3D vector information can be given one of two ways. You might be given alpha, beta, and gamma along with the magnitude of the vector. These refer specifically to the angle the vector makes with the x, y, and z axis respectively in a three-dimensional space. These angles are called the coordinate direction angles. You might also be given the magnitude of the vector and the angles for a projected component of the vector. For example, the projected component of the vector on the xy plane makes the angle theta xy. This type of angle is called a projected angle. As a hint, alpha, beta, and gamma are exclusive to coordinate direction angles, but you should be able to differentiate between the two. You should also be able to geometrically work with both types of angles to change the vector into the Cartesian form to analyze your systems. This example is taken from Hibbler 15th edition. It's problem 583. The problem asks us to find the coordinate direction angles of vector F3, that's alpha, beta, and gamma, and also the magnitude of the resultant force. So this is a three-dimensional problem, but you can see that F1 and F2 are lying within the planes XY and YZ respectively, and F3 is in a three-dimensional space. Next, we look at the equations and assumptions that are required. But first, let's take a look at our system and just isolate the different forces so that we know what equations we need, what exactly we have. So to start with, we of course have our forces. We have our 800-pound force acting up and back. Then we have our 600-pound force acting to the right, and then we have the 700-pound force acting forward and to the right. Our 700-pound force is at 30 degrees, and our 600-pound is indicated by a small triangle, and that is a 3, 4, 5. We also are given the unit vector for our resultant force as the cosine of 30 degrees j plus sine 30 degrees k. So we'll just assign that to the right and say that FR is also to the right. Of course, because remember that the unit vector is in the same direction or the same sense as the vector that it's representing. So the equations that we'll be using is the vector resultant force is equal to the magnitude of the resultant force times the unit vector of our resultant in the direction of our resultant force. That's equal to our magnitude in the x direction times the cosine of alpha times I, or the unit vector in the x direction, plus the magnitude of in the y direction times cosine beta times j hat, which again is the unit vector in the y direction, plus the magnitude in the z direction times cosine gamma times k caret, which is the unit vector in the z direction. All of these are assumed to be positive. If it comes out negative, then we've made the wrong assumption, but we'll just change the sign. And that is equal to the magnitude in the x direction times I caret plus magnitude in the y direction times j caret plus the magnitude in the z direction times j caret. Then we can also say, or we also know, that the sum of our vectors is equal to the resultant vector. Okay, again, those vectors are they each have an ij and a k component, and therefore fr also is ijk. So if we substitute also our first equation into this equation, then we get the magnitude of our resultant force, which is what we're looking for, one of the problems, times the unit vector of our resultant force is equal to the vector f1 plus the vector f2 plus vector f3. And lastly, we need an equation that relates our alpha, beta, and gamma. And so we have cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And just to reiterate, alpha, beta, and gamma are very specifically referring to angles within the three-dimensional space with respect to the vector that you're looking for. The solution method that we'll follow is we'll first isolate each one of the forces and resolve them into their ijk components. And we're going to go ahead and use, of course, Cartesian notation because it's a little bit easier. So we'll start with F1. We know that F1 is only in the xy plane. Therefore, you're only going to have an I and a j component. This is a good time to remind you of the sine, cosine, tangent relationships. That is SOHCAHTOA. The sine of theta is equal to the opposite length divided by the hypotenuse length. The cosine of theta is equal to the adjacent length divided by the hypotenuse length. And the tangent of theta is equal to the opposite length divided by the adjacent length. And just as a reminder, opposite refers to the length opposite the angle that you have. Adjacent means the length next to the angle that you have. So in this picture, even though you have x is adjacent to 30, as is 700 is also adjacent to 30, but 700 is a hypotenuse. So adjacent is next to, but then separately you have the hypotenuse. So the vector F1 is equal to 700 pounds times cosine 30 degrees plus I caret plus 700 pounds sine 30 degrees plus j caret. And you can add the 0 in the k caret direction. This is equal to 606.22 I caret plus 350 j caret pounds. We'll do the same analysis with our vector 2, which is 600 pounds. So again, this time we're looking at vector 2 is only in the YZ plane. Therefore, we'll only have a j and a k unit vector. In this force, we're going to apply the similar triangles or the smaller triangle notation, which is that the ratio between the vertical and the hypotenuse of the smaller triangle is the same as a ratio of the vertical and the hypotenuse on the larger triangle, which is made with the vector F2 and the y axis. Similarly, the relationship between the horizontal component of the smaller triangle and the hypotenuse is equal to the horizontal of the larger component and the hypotenuse. So you'll see that we have the vector f is equal to 0 in the I component, or the x direction, plus 4/5 times 600j plus 3/5 times 600k. So then we have our second vector f in the j and k components. Now we'll look at vector f3. Here we don't know alpha, beta, and gamma, but vector f3 is in a three-dimensional plane, which means it has all three components, I, j, and k. Therefore, when we write our f3, we'll be using the equation that we wrote for the resultant force is equal to f in the x direction times cosine alpha I caret plus f in the y direction times cosine beta j caret plus f in the z direction times cosine gamma k caret. So we have f being 800 in the x direction is 800 cosine alpha. So 800 cosine alpha I caret plus 800 cosine beta j caret plus 800 cosine gamma k caret. Now we can apply the FR, or our resultant force magnitude, times the unit vector in the same sense or direction of our resultant force is equal to the sum of the vectors F1, F2, and F3. So we're looking for the magnitude FR, but we are given the unit vector in the FR direction, which is cosine theta degrees times j caret plus sine theta degrees times k caret. Then we solved for our vector in the Cartesian notation of 1. That is 606.22 I caret plus 350 j caret, and that's pounds. Now we add our second vector, which is 480 j caret plus 360 k caret, that quantity pound. And then lastly, our vector f3, which is 800 cosine alpha I caret plus 800 cosine beta j caret plus 800 cosine gamma k caret, all in pounds. Now we're going to isolate the components and solve. If there's only one unknown, of course, we can complete the solve, or we can just reduce it and solve later. So to start with the I, on the left-hand side, which is our resultant force, there's no I component, so we'll have 0. And then on the right-hand side, we have the I component in the first vector, which is 606.22 I caret, plus the I component in the third vector. There's no I component in the second there, so that's plus 800 cosine alpha I caret. Then we'll isolate the j's. On the left-hand side on j, we have cosine 30 degrees j times FR, which is 0.86603 FRJ caret. And then on the right-hand side, in the first vector, we have 350 j caret. In the second vector, we have 480 j caret. And in the third vector, we have 800 cosine beta j caret. So in this case, we can solve down because we'll have to solve for our resultant force, but we'll solve down and have cosine beta on the left-hand side, just like we did for I, cosine alpha on the left-hand side. So looking at k, we have in the first, on the left-hand side, we have sine 30 degrees k caret. So we have 0.5 FR k caret equals, in the first component, there's no k. In the second component, there's 360 k caret. And in the third component, it's plus 800 cosine gamma k caret. So solving that down, we have 800 cosine gamma equals 0.5 FR minus 360. Now, since we have the relationship cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1, then let's go ahead and square these three isolated components and add them up so that we can pull out that entire term. So squaring I, we get 800 squared cosine squared alpha equals 367,500. Squaring J, we have 800 squared cosine squared beta equals, and I've already squared this out, it equals 0.75 FR squared minus 1,437.6 FR plus 688,900. Then squaring K, I also calculated that out, so it's 800 squared cosine squared gamma plus or equals 0.25 FR squared minus 360 FR plus 129,600. So when we add that up, on the left-hand side, we get 800 squared cosine squared alpha plus 800 squared cosine squared beta plus 800 squared cosine squared gamma. Now, if I pull 800 squared out, I'm going to have my relationship of the cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. And that's what I'm going for. Adding the right-hand side, I get 1 FR squared minus 1,797.6 FR plus 1,186,000. So now I'm substituting in my relationship for the cosine squared, and I get 800 squared times 1 equals FR squared minus 1797.6 FR plus 1,186,000. So moving my 800 squared to the other side, I now have a second order polynomial, which I can solve for by roots. You can use anything, like you can use your calculator, but if I were you, I would also get used to using the quadratic equation relationship, which is negative b plus or minus the square root of b squared minus 4ac divided by 2a. So you're going to have two possible quantities for the magnitude of the resultant force. The first will be 1,410.5 pounds, and the second will be 387.096 pounds. So again, if you're using the quadratic equation, your A will be 1, your B will be negative 179 or negative 1,797.6, and your C will be positive 546,000. Now we can solve for alpha, beta, and gamma. Alpha is pretty simple. We'll use our first equation. 800 cosine alpha equals negative 606.22. So we just move our 800 to the other side by dividing, and we get alpha is equal to 139 degrees. For beta and gamma, since they're both dependent on the resultant force or the magnitude of the resultant force, you'll have to work them twice. One with the magnitude 1,410.5 and the other with the magnitude 387.1. So we'll work it twice. The first time we have 800 cosine beta equals 0.86603 times the magnitude, or 1,410.5 minus 830. Of course, working out the algebra, we get beta equals 60.7 degrees. Using the other equation for gamma, we have 800 cosine gamma equals 0.5 times 1,410.5 minus 360, and we get gamma is equal to 64.4. We'll do the same thing with our 387.1 pounds. Algebraically, we just substitute in 387 for FR and work the algebra. For the beta, we get 128 degrees, and for gamma, we get 102 degrees.